Okay, this lecture is about the principles of ECG. When I say principles of ECG, it means that what is the theory behind the biophysical theory behind the ECG. We're not going to talk about parameters of a normal ECG. How do you use ECG to diagnose certain heart issues and things like that is out of the scope of this lecture, and I assume that you know how a basic ECG system is set up. How do you connect the wires or the electrodes to the patient, and what does the regular ECG trace look like? So if you do not remember those, go back and look your notes. Now we have to remember the previous lecture that a compound action potential is an action potential that you record from outside of the cell, from outside of the tissue. However, the reason for this potential to occur is the action potentials happening in the cells of that tissue. However, if the whole tissue has cells which are depolarized, or the whole tissue is polarized, you cannot record any potential outside this tissue. The potential will be almost zero. So you need a situation where part of this organ or the tissue is depolarized, part of the tissue is polarized. This is the only condition where you can get electrical effect, electrical field outside the tissue. And that electrical field is thought to be created by a single dipole. So in the cardiac tissue, during the spread of action potential, part of the cardiac tissue is polarized and part of the cardiac tissue is depolarized. So a net tissue dipole, electrical dipole, forms, and this is called cardiac dipole. This dipole during the cardiac cycle, single cardiac cycle, changes its orientation and its size, as we will see in detail now. Just a quick reminder that in the heart, action potential starts in this atrial node and spreads through the atria first. Then, when it comes to atrioventricular node, it slows down a bit, and then it spreads to his Purkinje system throughout the septum, and then it starts to spread to the ventricles. The left ventricle, as it has a larger muscle mass, it takes longer for the left ventricle to depolarize. So the depolarization in the right ventricle ends first. The action potential spread continues in the left ventricle a little bit longer, and at the end of this, the whole ventricle becomes depolarized. Then the repolarization of the tissue starts, and it repeats itself endlessly. I mean, almost endlessly. When the action potential is spreading in the atria, in the ECG you see the P wave. When the action potential starts to spread to ventricles, you will see the QRS complex. There is a silent period between the P wave and the QRS complex, because in between, the only tissue that has action potential is the atrioventricular node. The whole atrium is depolarized, so it does not form any net dipole, and the ventricle is completely polarized, so it does not form any net dipole. There is a non-connective tissue between the atrium and the ventricles, so between an atrium and ventricles there is no net dipole. The only part that may create a dipole is the AV node, which is very small to detect. After this spread into the whole ventricle of the action potential, at the end, which means the QRS complex is terminated or reaches its end, then after a delay, you will record zero potential again, because the whole ventricle is depolarized. It doesn't form any net dipole. The repolarization starts. The repolarization wave causes the T wave in ECG. So let's take a look at the simplified version of action potential spread throughout the heart and what kind of a net dipole this creates. The depolarized tissue is shown with a gray area. The dipole of the heart, or the cardiac dipole, is shown with white. The size of the dipole shows the strength of it, and also you can see the orientation of the dipole at that instant. So the depolarization, or the action potential wave, spreads through the atrium, and when it comes to the atrioventricular node, it delays a little bit, and then it spreads to the his Purkinje system in the second picture. However, the first tissue that is depolarized is the septum. In the septum, the depolarization wave spreads from left to the right of the patient. Then it spreads to the apex, and then the right ventricle depolarizes. The whole right ventricle gets depolarized, but at that instance, left ventricle still continues to depolarize. The depolarization wave is still spreading through the left ventricle because, as we said before, the left ventricle has a larger muscle mass. So the dipole, cardiac dipole, turns left and it gets bigger. At the end of the left ventricle depolarization, the cardiac dipole, turns left quite a bit, but its size continues to shrink because the border between the depolarized and polarized tissue gets smaller and smaller, which means that the dipole, which is created by that border, as we seen before, the size of that border gets smaller and smaller, so the dipole gets smaller and smaller. When the whole ventricle, left and right ventricles, depolarized, there is no net dipole anymore. So after that, the repolarization wave comes. The second piece of information or concept we need is to understand ECG is the Eindhoven Theory. Eindhoven is the first person who invented ECG and used it as a diagnostic tool, and he also explained the theory behind the ECG. His model is that the electrodes you connect to a patient, for example, on the left hand, the right hand, and the foot, forms a triangle which has equal sides. And center of this triangle is the heart. Heart has a dipole, single net dipole, as we discussed before. And this dipole changes orientation and size, and that's why the potentials you measure from these electrodes are changing. As you measure potential differences, you pick pairs of electrodes and make measurements from them. If you take the left and right hands, the potential you record or measure from those two is called first derivation. If you take the right hand and the foot, you end up with the second derivation. It's called second derivation. If you take the left hand and the foot, it's called the third derivation. There are also augmented derivations. Augmented derivations are created as follows. If you take, let's give an example for the AVR. AVR is the measurement you make between the right hand and the electrode that you created by connecting the feet and the left hand, the other two electrodes. You connect them and end up with a single electrode, and you measure the potential difference between this connected point and the right hand. It's called AVR. The AVL and AVF is created using such a method. These are called augmented derivations. So, and at the end, the standard ECG has 6 derivations. What is the relation between the dipole, the cardiac dipole, and the potential difference that you're going to measure from those pairs of electrodes, which are called the derivations. So the Eindhoven theory says that the potential difference, the strength of the potential difference between you're going to measure from a derivation will be proportional to the projection of the cardiac dipole onto that derivation axis. On the illustration, you can see two examples. One for the third derivation, and the second is for the AVR augmented derivation. In the picture, the illustration, the cardiac dipole is shown in black, and the projections onto the third derivation axis and the AVR axis is shown in red. So whatever potential you're going to measure from these derivations will be proportional to these projection vectors. You can immediately see that the size of the projection vectors is not only correlated to the size of the cardiac dipole, but they also depend on the orientation of the cardiac dipole, or the orientation of the cardiac dipole in relation to the axes that you make the measurement from. For example, if the dipole is perpendicular to the axes you're going to measure from, for example, to the third derivation, there will be no potential that can be recorded from the third derivation, even though the dipole, or heart dipole, is still quite strong. So the axis, the rotation of the dipole is also an important factor which determines the strength of the potential that you're going to measure from any derivation. What will be the sign of the measured potential? So the rule is, if the projection vector directs towards the positive electrode, you'll end up recording a positive potential. If it directs towards the negative electrode, you'll end up with measuring a negative potential. So it's important how you connect those electrodes. If you switch the polarity of the electrodes, then you'll end up with, instead of a negative potential, you'll end up with a positive potential. In order to avoid this confusion, you have to connect the electrodes properly. That in this graph, you can see the proper way to connect electrodes to the patient. So let's combine these two information together and see what kind of potential are we going to measure from the three basic derivations.